Good morning, everybody. My name is Jack Liu, the manager for the NIOSH Musculoskeletal Health Cross-Sector Program. It's my pleasure to introduce today's speaker, Dr. SangHyun Lee, to give a presentation on a computer vision-based automatic ergonomic risk assessment system. Dr. Lee is an associate professor in the Department of Civil and Environmental Engineering, University of Michigan. Dr. Lee has over 170 publications and has written 2 books. He has received numerous awards for his contributions to science, including the recent Thomas Waters Awards for the Best Manual Materials Handling Presentation at Applied Ergonomics Conference in 2018. Dr. Lee will be repeating this award-winning AEC presentation and adding more information on how to use a smartphone to conduct ergonomic assessments in a workplace. Welcome, Dr. Lee.
Thank you, Jack. Hi, we had a little bit of process, but I'm glad it is working. It is quite an honor to be here and present, particularly given that I received the Tom Waters Award several months ago. So it is great, really great honor, and I hope it can discuss kind of the emerging and new technologies coming into the market and the industry. Let me talk about, so basically I would like to talk and discuss this new emerging technologies and what we can do for the ergonomic field. So my presentation will be smartphone-based, basically computer vision-based ergonomic risk assessment. Okay, so I don't think I need to repeat about the importance and the seriousness of the musculoskeletal disorders in the United States. So basically, many workers suffer from, and a lot of money we spend to remedy this situation. And one of the things that we do to address the musculoskeletal disorder is basically ergonomic risk assessment. I have a chance to talk with more than 100 ergonomic practitioners to learn about what they are doing for ergonomic risk assessment. This is kind of my very simple view of basically what they are trying to do. So when they have the job in the plant, for example, they go to the site and observe how and what worker is doing. Or sometimes they take a video and they come back to the office and figure it out basically basic level assessment. This basic level assessment is basically to identify ergonomic risk. So we can say that it is more about the risk and job screening, meaning that we would like to identify which job is causing the problem. Then we are going to narrow down the scope and do in-depth analysis. And then if you want to fix something, you will go with a very sophisticated analysis tool to identify how we can address this issue. When we look at this process, one of the major limitations is basically manual observation. You have to manually observe. You have to go to the site and see how worker is doing, or you have to take a video and you have to play back like more than 10 times to figure it out what kind of input you need for basic level of risk assessment. So it's a time consuming. Let's say we have like a 1 or 3 minute, 5 minute job cycle. People usually spend half an hour, even they spend 1 hour to get all the info for basic level risk assessment. Also, it is a limited coverage, meaning that yes, I would like to study and screen all the jobs in my plant, but basically I don't have a manpower to this. So when I talk with the several big manufacturing, the safety managers, they are saying we just cover 10 to 20%. We have to rely on our some injury report or some observation. So they would like to do ideally 100% coverage of the basic risk assessment, but simply it is not possible with the resource they have. Also, sometimes training needed. Yes, manual observation sounds like a simple task. They can hire high school student and undergraduate student as an intern, but it also requires a lot of training. Also, when I work with professional ergonomists, we actually find that they have a different way to identify basic risk assessment. For example, the way that they measure back bending angles, it depends on who basically is observing what workers doing. So it is not consistent at all. So what we are trying to do, what we are hoping is say, okay, if there is a motion capture system, we may automate this process, right? So there are a lot of different and commercial motion capture systems which has been widely used in the movie industry and gaming industry. Also, a lot of people in the ergonomics and biomechanics trying to use motion capture to automate this process. I'm not talking about the commercial system. Basically, we have optical and inertial measurement unit systems for motion capture. They are very accurate, and I also saw that what you are using in your lab in NIOSH, but basically it is very accurate, and this is where the performance that we can get is very accurate. Also, it is less affected by line of sight, right? Because, for example, optical system, you use at least 8 cameras or even 16 cameras and 30 cameras. Or if you use the IMU system, you are going to put the sensors on the people's body part, so less affected by line of sight. So those are all great, really great, work great. However, there are some cons for ergonomic risk assessment. Let's say these great tools you would like to apply to ergonomic risk assessment, particularly in the field. Risk screening, you need to get the data from the field. So let's say, so there are some cons when you apply these technologies to the field for ergonomic risk assessment. First of all, the price dropped down recently, but still it is expensive. And more problem is it's a little bit cumbersome to be applied to the field. Basically, you have to put the markers or sensors to each body part, each body joint, or certain should have to be worn. So it is not convenient for you to use to the field. Also, in need for certain systems need calibration time. I don't know if you have experience. Some systems basically requires your T-pose in the beginning and ask them to walk around. Immediately you apply this time to the field and stop the work and ask for them to do to the certain pose to get the system going. It is not that desirable situation. Also, it often needs a control setting, right? For example, optical system. The camera has to be fixed. You need to basically left. It is very difficult to be applied to the field. Also, only one subject at a time, right? You would like to have a multiple use, but it is not that easy because the system is very hard to configure in the beginning. So going back to our original slide, so this is ergonomic risk, and we talked about the need for motion capture. Then how about just motion capture with a smartphone? Okay, everybody nowadays has a smartphone. Smartphone has a basically video camera. Then why don't we just use the motion capture, the smartphone for the motion capture? That's my major motivation. So why? So not interfering with the ongoing work. Let's say one day you walk around your job site in the plant and you see that something is awkward, and you can just pull your smartphone and just record the video. No marker sensors are needed. Just you are going to use your smartphone, so you don't have to interfere with what workers are using. So also very affordable. You don't need any sensors, so no hard work is required. Also very easy to use. The computer, basically the software, will figure it out what you are going to do. And also no setup time. It doesn't require any T-pose for setup time, so you can just record the video and get the data. And also it can be multiple use, meaning that many people have just smartphones, so many people just can simultaneously walk around the site and get the data. Also, no need to be stationary, meaning that some system requires fixed camera, but this one doesn't have to be stationary, meaning that let's say you are recording with your smartphone, and then you don't have to fix the smartphone. So you can actually work around. Let's say you see the line of sight here, so you use your smartphone. Now it is already blocked, and you can slowly move around. Of course, if you swing like this one and move very fast, there is no way to catch up. But at least you can slowly move around, and you have a just natural vibration from hand. It doesn't really matter. So it actually allows to be very flexible to walk around the site and to get the data that we need. So how this can be applied? So what we are talking about right now is ergonomic posture analysis, like OWAS, RULA, and REBA, etc. There are many different ergonomic posture analysis tools, or certain company has their own tools developed for their own needs. But when we take a look at most of the tools they use for ergonomic posture analysis, they require these 4 pieces of basic information: posture classification, is it back bending or arm reaching, frequency, how often they bend their back, duration, once they bend their back, what is the duration of the back bending, and severity like back bending angle. So those are basic 4 pieces of information that needed for most of the ergonomic posture analysis tools. So that's what we provide. Can you play the first video? So now you can see that what we try to do is that I'm supposed to see the video, right? Can you play? Yeah, okay. Okay. I don't.
Another window.
Yeah, I don't think the audio is synced. Okay, I'll try. Yeah. Yeah. Can you play the one more time? Sorry for the webinar audience. The audience here has not been able to see the video, so we are playing again. Sorry about that. So here we can see that the typical skeleton has been generated. So the way it works is that basically we have thousands and thousands of images, and we annotate them as which one is shoulder, which one is a wrist, which one is a back, and then computer identifies what kind of the image patterns are there, and then once you see the real-world video, they recognize which one is that. Then we connect them, and we use the kinematics to make sure that that is like a skeleton. So we use one of the tools like a REBA. So you can see that, for example, we use the REBA standard to identify which one is red, which one is green, yellow, and which one is gray. For example, for back, it is a bending more than 60 degrees, we just put the red. So it can be, what I'm trying to show is that it can be customized based on what kind of tool they use. And can you play the second video? And then once we have a skeleton, so basically now we can get a lot of the detailed information. So for example, now you can see that frame by frame, typically smartphone has a 29 frames per second. And frame by frame, you are getting all the different angles for the different body parts. Right arm, left arm, back bending. So we can identify what is the angle, but at the same time, easily we can calculate maximum angle, frequency, and duration. So here also you can see that whatever threshold that you are interested in, you can put the different threshold, and we are just going to identify because we provide raw data frame by frame. Thank you. Now, can you play third video? Then we can use in many different ways, and one of the ways that we are trying to use is a risk comparison across different jobs. So you can just collect different videos, meaning different jobs, and then it can identify, okay, in terms of left knee, which one has a more hazard, or back bending, which job is more hazard, or how's the proportion of the safe and the cautious and the hazardous. So you can have cross comparison across the different job cycles. So how does it work? So also one thing that I would like to mention is that, of course, the processing unit in the smartphone at this time is very limited. So the way it works is that smartphone captures the video, and then it sends it to our cloud system, and then do all the analysis, and going back to our phone with all the skeleton, superimpose the video as well as raw data. It can get the text file or Excel file or whatever format that you want. So let's see what is kind of the accuracy level comparing with the ergonomic practitioners. Again, this application is to make sure that we can do basic risk assessment. So our concern at this time is how's the performance of this technology with ergonomic practitioners. So we used the two videos, each 72-second video, and one is a side view or one is a diagonal view. Because depending on the view angle, the way the measure angle can be different. So we would like to make sure what is a side level accuracy from human ergonomic practitioners and our technology, as well as a diagonal, like a 30 degrees. And then what we did is that based on REBA, we ask them, the ergonomic practitioners, to measure frequency and duration per each body angle category. So for example, back bending, if you see that back bending angle is greater than 60 degrees, measure frequency. At the same time, when you measure frequency, also measure the duration. The baseline that we use is the IMU-based motion capture system as a baseline. Then we ask them to pick up, calculate frequency and duration for each category. 27 ergonomic practitioners participate in this study, and 7 subjects has less than 2 years of experience, and 20 subjects has more than 2 years experience. And of course, the ergonomic practitioners can play the video back as many as they want. So can you play the first video in the slide 14? So this is a side view. So this is a part of the 72-second video, but you will see that when they lift something, it is be more about the side view. And also you can see the skeleton has been generated. We use the REBA for this purpose. So all the different color coded are depending upon the REBA classification. Sometimes there are occlusions, then we miscalculate, misidentify joint, but as soon as it shows, or we have an algorithm to have a best guess for the hidden body part. So we comparison with the frequency and duration. So in terms of the frequency, among the older subjects, our technology ranked as number 1. The metric they use is the average number of miscount per body joint. So on average, our technology has 0.25 miscount per body joint, but the people usually have a 1.5 times for each body joint. And the duration, still our technology ranked as number 1, and on average, our miscalculation is a 0.33, but practitioners usually have a 5 seconds of error for each body joint. Can you play the second video? Actually, first video on the page, slide number 15. So this is more about the diagonal view. When you actually see that people lift something, it will be more like a diagonal view, which is a little bit skewed. Can you stop and play again? I don't think it is showing on the screen. Okay, but it is very similar to what you have seen, a little bit different view. In terms of the diagonal view, the frequency is that our technology is ranked number 3, on average slightly better than practitioners. For example, 1.33 miscount per body joint, while the practitioners have a 1.89 miscount per body joint. And the duration, our technology ranked the 7th, and on average slightly better than the practitioners. So when we compare the accuracy of our technology with ergonomic practitioners, at least we can safely say that we have a human level accuracy. Indeed, it's actually better, but to be conservative, at least we have a human level accuracy, but it's much faster. The practitioners took almost 16 minutes on average for 72-second video. But we, including all the Wi-Fi connection and everything, we took like less than 1.5 minutes, so at least 10 times faster than what people usually do. So it is still ongoing with more subjects, but you have a sense of what kind of accuracy level and how fast it is comparing with ergonomic practitioners. Now, so let me go back to this ergonomic risk assessment, the motivation slide. So now we have been talking about the motion capture with the smartphone for basic level assessment. Now you notice that it is all about the 2D. So that is why it is at this time to limit it to basic level risk assessment. But in the end, what we want to do is an in-depth analysis, meaning that why don't we have a 3D with a smartphone that will actually can open the door to be used for more in-depth analysis, sophisticated analysis, try to identify how we can fix this problem. Can you play first video in the slide 19? So this is the video that we collected in our lab. Okay, let me see. Typical lifting task. Somehow I don't, yes, it's showing. Very typical lifting task. Can you play the second video on the slide 19? So this is 3D skeleton generated only from the smartphone. So now how can we use this 3D skeleton for further analysis? One of the things that I try to show how this can be applied to the ergonomic tool is that, of course, the NIOSH lifting station. So I try to semi-automate NIOSH lifting occasion with the 3D skeleton that we generated. So basically, we don't need to measure any horizontal and vertical locations. We don't need to measure vertical travel distance, asymmetric angle, and frequency. So what we need to measure is the weight of the object. By the way, weight of object also can be automated, because if you have a hand probe object that you are dealing with in the plant, actually we can identify what object is, and we can easily associate with the weight. So weight also has a potential to be automated down the road. Something that we still need as an input is a coupling. Coupling is a very sophisticated, so it requires further technology advancement, but at this stage, we are getting just the input about the coupling. But if you may know, know better than me that coupling has the least impact on the lifting index when we calculate the lifting index. And then we also need height information, because NIOSH lifting indication is a little bit different from what you saw from postural ergonomic analysis, because you need to measure distance. So we are getting workers' height to infer all the distance that needed for NIOSH lifting station. So one way, there are two ways that we can use this NIOSH lifting station. The first way is, like what you do, you can pick up origin and destination, then we will calculate all necessary input. It's a straightforward, right? Because now you have two images as an origin and destination, and we can identify angles, but at the same time, we can measure the distance. Or you can let the system to pick up the origin and destination. It's a slightly different. So in this case, you actually don't need to put the origin and destination. You can just put the video. And then our system will figure it out frame by frame, calculate everything. So for example, the first step is we are going to identify the product of the multipliers except the vertical travel distance, frame by frame. And then, because now we have a vertical location, we can also identify vertical travel distance of each frame. So for example, a certain frame like you see here, we know the minimum vertical location and maximum vertical location. You can get the difference and take up maximum to give the least distance multiplier. and then you multiply 1 and 2, you will get recommended weight limit or lifting index frame by frame basis. So if you pick up manually origin and destination, we are going to identify which one has the highest lifting index, or if you let our system can pick up lifting index, we are going to identify slightly different from what you're expecting from your destination. So this is because, for example, when you lift something and place it in the higher position, actually what people do is you reach high and then put the destination. So we are actually capturing how much people are trying to lift higher to place something on the destination. So this is the matter of choice that what kind of things that you would like to do, but this one certainly needs discussion about how we can best use of technology for NIOSH lifting patient. So this is an ongoing study, but we just measured comparison with the actual measurement. We used the 3 subjects, short and medium and tall person. And ground truth is the actual measurement for origin and destination, and task is the material lifting. So when we manually pick up an origin and destination, mean difference in lifting index is 0.1. So if you want to use this one as a very sophisticated analysis, this difference may be high, but if you use it for risk screening, I talked to several of the practitioners, they are acceptable, but it is just different the choice of the criteria that you apply. But when actually practitioners use this NIOSH lift indication to the field, many cases they don't actually take measuring the parameters in the origin and destination. They just guess, and sometimes they just infer from certain the object height and etc. So this is what we are getting when you manually pick up an origin and destination. And when we automatically picking up origin and destination, mean difference in lifting index is 0.02, but this difference doesn't really show any accuracy. It just shows that certain the difference between what we automatically pick up lifting index versus what the actual lifting index. So we talked about the 3D, and this is where we are heading right now. What I'm interested in the end is I would like to do on-site biomechanical analysis. You may notice what I'm interested in is a certain tool that can be applied to the field without any big problems. So I'm trying to go to interaction for on-site biomechanical analysis. Can you play the video in slide 23, this one? Okay, I hope you can see the video. So basically what we developed a prototype system which I extract 3D skeleton, and then we connect with the biomechanical analysis tool. Here we use the 3D SSPP developed by University of Michigan Center for Ergonomics, and we connect it to 3D SSPP engine to identify biomechanical load for each body part. So this is where we are heading, where I am heading right now. But at the same time, I try to approximate measurement or approximate guess of the force patterns from the video images. That's what we are working on right now. So we try to fully automate on-site biomechanical analysis only with the video cameras or smartphone. So let me draw conclusions. So smartphone-based or vision-based ergonomic risk assessment enables quick and easy assessment without any special equipment, and it is compatible with the existing risk assessment tool. Also, I would like to make sure at this time we are really targeting the risk screening purposes. And 3D skeleton also can be generated for more in-depth analysis. I think it can offer more opportunities for sophisticated analysis for the ergonomics. And the last one is we are moving towards smartphone-based on-site biomechanical analysis, automating force prediction at the same time with a 3D skeleton. So I would like to acknowledge my sponsors, National Science Foundation and College of Engineering, the Amtrak program, as well as Toyota. And if you have any further questions, feel free to talk with me, and I'll be happy to answer any question that you have.
Thank you, Dr. Lee, for your wonderful presentation. And I apologize, especially for the audience on the web, that due to the Adobe Connect limitations and streaming video on the web is extremely slow. So a lot of video we have shown is kind of choppy. So now we have some 20 minutes left to open up the questions, and we'd like to open up the question to the web. Any audience? Okay, so Jessica have not seen any written questions. Okay. Here's the one.
Okay, so the first one that we got says, what are the error differences on the smartphone approaches relative to conventional motion capture, particularly during axial trunk rotation?
Yes, so we also measured, we compared what smartphone can produce and what traditional sophisticated high-end motion capture system provide. Something that I would like to make sure is, sorry for my posture in the audience here, I try to be close to the mic. So what we are trying to do is the 2D, when we compare to 2D, and 2D is, of course, we have a lot of the view angle distortion. So with the commercial and sophisticated analysis, we can see that the very high correlation, but if you put me into the corner and ask me what is the angle difference, I would say around 10 degrees in general. So that is the kind of the angle difference that we are getting in case of when we compare 2D technology. 3D technology, our preliminary analysis shows that around 5 degrees. But one thing also I would like to mention, I don't know if some have a lot of experience using motion capture system. When you use the commercial motion capture system, one of the problems that I experience is that it actually loses a lot of data. So it needs a lot of post-processing. So giving a lot of post-processing effort, then yes, once we get the data, it is very accurate, but getting the accurate data is a little bit challenging. So that's something that I want you to consider about this one.
Okay, so the next question is, has any of your work been published in journal articles, and if so, can we get the citations?
Yes, my earlier work has been published. Earlier work means 7 years and 6 years work about all the computer vision. And since then, I actually haven't published in journal articles because this technology was picked up by a certain agency, great potential for commercialization. Then it has all the patent issues and all that kind of issue. So actually, I didn't publish journal articles about the technology. I apologize for this one, but we are trying to commercialize and widely deploy to help people for risk screening. So it has a little bit different, the purpose and route for this one, which I hope you can understand. But for my very recent work, 2D classification, 3D work hasn't been published, but we are producing white paper for the company who commercialize this 2D technology. We are putting the validation for what kind of correlation that we are getting. We are creating a white paper for this one.
Okay, and the next question, do you plan to extend this technology for real-time risk assessment?
Yes, that's what I'm interested in. Currently, if you recall my slide, 2D technology, 1 minute, 72-second video, having 1.5 minutes, less than 1.5 minutes, typically 1 minute. But in the end, what I want is that when you walk around your job site with your smartphone and you see that something awkward, and you just record it, and then you can actually see the result, then you can provide a feedback to the workers or use for whatever that you are interested in. I don't think it is going to be truly real time, but near real time, within a minute, whatever the result that you are interested in is what we are trying to do. So we are heading into this direction.
Okay, thank you. And there's one last question, and then we'll jump to the audience. Is there anything in the future that will be developed for capturing hand, wrist, and finger postures?
this is a great question. This is a great question. Let me put it this way. In general, computer vision, what the technology we are talking about is basically when we see, we can identify that. So if we cannot see, we cannot identify. At this time, we are focusing, so to speak, growth posture, because we are thinking about there are not many situations people put the camera on the hand and wrist and etc. So we are focusing on the growth posture at this time. But once we have a line of sight of detailed hand movement, it's the same principle basically. However, I would like to be very cautious about finger movement because hand and finger model is a complete, very sophisticated one. So that requires further research, but in general, wrist movement, wrist flexion, and those kind of things, as long as you have a line of sight, as long as you have a place to put the camera, it can work.
Okay, do you have any questions from the live audience in Cincinnati?
Dr. Lee, when you're using the 3D SSP analysis, one of the later slides you showed the ladder movement. Is that all video also captured from a smartphone for the analysis?
Yes, and we also use the very cheap 3D depth sensor to scan the side. It is not accurate. Let me see if I can. That should be just snapshot. Yes. So here, 3 skeleton is from the video, and the ladder actually you can see the very rough scanning of the job site. That is, we use the very cheap sensor to get the just idea of what kind of job site looks like, and then we superimpose skeleton to the rough scanned data, the job site. Yes.
Anybody else?
Dr. Lee, it was a great presentation. Thank you.
you.
I have a quick question about the angles. When you're just detecting the angle with using the smartphone, and as an output, you're giving the high risk, whether they're in the medium risk or low risk, right?
Yes.
For the REBA and NIOSH listing equation, are you giving the scores at the end as an output too, or is it just only like they're in the high risk or medium risk or low risk?
Okay, that is only for just as a one simple example. So we just say high risk, medium risk, low risk based on REBA classification. So in the end, what we are trying to do is we can automate all the different body parts and then we can provide a score. So for example, we are automating the Liberty Mutual Snook tables right now. That's possible. Then once we get the raw data, electric conversion, then we will get the scores or population will supposed to get injury will be provided from Liberty Mutual tables, for example. So this is just one example, but because we have a raw data, we can customize and to fit the system or scores that you are interested in. So that's the point of the test slide. And to summary, going back to your question, yes, we can do.
Thank you.
Yeah, thanks.
Okay, we have one more online question. Have you used different smartphones, and are there differences in the capture data?
No. So basically what we are talking about is a smartphone is just one device. We are talking about actually the more accurate term should be digital video camera. So the reason that I'm using smartphone is a smartphone, everybody uses it as a video, which has a function of a video camera, but at the same time it can have a app and it can have a wireless connection, so sending and communicating data. That's why I use the smartphone. But basically what we need is ordinary digital video camera. So most of smartphone cameras nowadays, anything that you have, as long as you purchase it within 5 or 6 years, most of the video camera in the smartphone is a high definition quality. So meaning that typically at least 29 frames per second. So that's what we are using. But so no difference in the different types of smartphone. As long as you purchased not long ago, as long as you purchased recently, like within 5 years, so to speak.
So I have a question, Professor Lee, for you and other NIOSH colleagues maybe as well. Oh, it's sort of closer. Okay. There's so much promise in this technology, and it seems like a lot of the methods that practitioners have used in this field that were developed before these types of technologies were thought of, really. Is there some hindrance to advancing this by referencing things like REBA, RULA, even the NIOSH lifting equation to some extent? If you kind of relinquish those types of references, is there more opportunities with the technology?
This is a great question. This is actually what I have been thinking about and what I'm learning right now. So what I think, by the way, I'm not really trained for ergonomics from my undergraduate, something like that. So please pardon my ignorance if I say something stupid. But the way that I see, most of the tools looks like they are taking into account the difficulty of the data collection. They know it is very hard to collect the data. And so, for example, NIOSH lifting equation, there is a good justification why we have to pick up origin and destination. But we haven't really thought about we will be able to get the data frame by frame. It's like a 29 frames per second. We just thought that maybe we will have a certain shot of the stop side or just observation, how we can approximate to do analysis. That's kind of what I'm thinking when I take a look at the existing technology. It is no blame at all. That is what it is. That is what we have to overcome at that time. But what I'm saying is that now, let's imagine, we just get all the jobs work what people are working, basically. You have a surveillance camera. We have all the cameras. So data is not limited at all now. Then maybe this is a good time to think about how we can revamp what we used to do. Maybe something more easier way and something more deployable way can be devised. And that's something I'm very interested in. That's what I would like to learn from your experience. What kind of things that you can see this can open the new opportunity? Because now there is no limitation to get the data. This is a very minuscule data, 29 frames per second. We even don't have to use all the data, but now we have that kind of data, all the jobs and all the people, all the work, then what can you do? I think this is a really great time to think about because this is about computer vision. But even same as the wearable sensor that we are using right now, we are getting the data. Then what is the best convenient way that ergonomic practitioners can use the data? And what is a convenient tool? They don't have to even get the training. Once they just use technology, they are supposed to get credible result. I think this is open the great opportunities for us work together to think about how we can do or better or how can do more easier for the field practitioners. Thank you.
Thank you for the presentation. I'm wondering, it looks like you might be getting really close to be able to do this analysis real time with real-time video streaming. I'm just thinking there's a lot of opportunities that would open up with that capability.
Yes.
And whether or not you're pursuing them.
Yes, and I'm also only show the ergonomic perspective, but also actually my earlier work started from identifying awkward posture, unsafe behaviors. And this is also still I'm working for the construction workers, like unsafe behavior, or they are close to the crane, we are identifying. So yes, we are getting to the almost the near real time. But at the same time, what I'm working on, ergonomics is a little bit different because it's a cumulative injury, so we can do post fixing later. But something, when we identify unsafe behavior, we have to fix it right away because it can be just near miss, but there is a high chance that it can be connected to near fall and etc. So with the vision, actually, what I'm working beyond the near real time is actually prediction. So I would like to predict because we have a lot of data is coming. A lot of data coming, so we are trying to have a near-time understanding, so to speak, at this time. But because of the data we are getting, actually we can predict. We don't have to predict 10 minutes, 20 minutes. We just need to predict 2 to 5 seconds to give immediate warning to the workers right away. So that's one of my projects that I'm doing in my lab. Once we have this pose data, can we predict the pose and how accurate that pose will be? And then can you predict unsafe behavior? Can you predict falls, fall and slip, so that we can provide a real-time warning. So that's something that I'm working in my lab right now. And that is I think the future direction that you will see from many, even though they use different technologies, that is kind of the trend and the future that I see in the down the road.
Okay, we have another question online. It says some companies do not allow their data collected on employees to upload to a cloud system for security purposes. Do you have the capability to upload to a specific computer or company server versus a cloud system?
Yes, I'm well aware of this problem. So because of the security issue, not many people are interested in third-party clouding service. So here, clouding service is just the example of the server, but it can be your own server, or it can be just your company server, or if you use a certain vendor's clouding service for your purpose, we can use that kind of server. So server, hardware, whatever computer, the clouding system doesn't really have to be third party. It can be just your choice, like your smartphone. You can choose whatever smartphone that you are interested in. Yeah.
Okay, that's the last question we had online, except for one technical question, which asked about this presentation being recorded and available for view later, which we have done through Adobe Connect. So we just wanted to let everyone know that it was recorded, and we'll find a way and a place to post it online so people can view.
Any other questions from the live audience? I have a question. I really like Brian's question about improving existing ergonomic risk assessment, because as a lifting researcher, I realize that we usually presume that the lifting point is the most stressful point. But now with the computer vision technology, we're opening up this opportunity to examine the entire course of lifting. Perhaps somewhere during the lifting, it's not really the lifting points in the beginning or destination of lift are the hazardous. Maybe during the lifting, somewhere during lifting could be very dangerous as well. So I think research is needed to validate this hypothesis. My questions for you will be, I noticed that you mentioned lifting frequency in your computer vision. I wonder your computer vision technology is able to automatically determine lifting frequency. If so, how?
Yeah, if that is a repetitive, basically we can identify, we can understand a certain posture of the start of the job, certain posture of the end of the job. If it is repeated multiple times, we can capture the frequency. So that's how, because lifting means that repeating same thing over and over again. So we can learn that which one, the repeating pattern starts, which point, and which is the end point, and we can automate. And going back to your first comment, and something that also I'm very interested in collaborating and discussing more about is NIOSH Composite Lifting Index. So I think it is really great too, but there is, like a NIOSH lifting composite lifting index, there may be something that you have all the different subtasks, and that is composed of the 10 or 12 and subtasks. Sometimes we have also mix of the subtasks. Some is in the cycle, some is not in cycle. Then maybe that kind of the video technology can be used to see that how we capture the risk in that kind of a little bit bearing cycle, situation. So those are something that I'm really interested in, say, what we can do together. So hope that answers your question for the second as well as the first comment.
Looks like we don't have additional question at this moment. I really appreciate everybody's attention and participation.